Welcome to the Complete Capacitor course. In this course, you'll learn everything about capacitors from basic concepts to advanced applications, including construction, working principle, AC and DC behavior, types, energy storage, power factor correction, power electronics, electric vehicles, renewable energy, testing, troubleshooting, and numerical problems. So, let's begin our journey into one of the most important components in electrical engineering. Module 1. Introduction to capacitors. Have you ever wondered, why does a ceiling fan run smoothly? How does your phone charger deliver stable power? Why don't LED lights flicker? How do EVs accelerate so quickly? The secret behind all of these is one tiny component, the capacitor. In this course, you'll learn what a capacitor is, how it works, why it's important, and where it's used, from basic concepts to real-world applications. Let's unlock the power of capacitors. What is a capacitor? A capacitor is an electrical component that stores electrical energy in the form of an electric field, unlike a battery, which stores energy through chemical reactions. A capacitor stores energy by separating electric charges. The basic structure of a capacitor consists of two conducting plates, one insulating material called the dielectric. When a voltage is applied across the plates, electrons accumulate on one plate while leaving the other plate. This creates an electric field between the plates, and energy is stored in that field. The amount of charge stored depends on the applied voltage, the capacitance value. Mathematically, Q is equal to C times V, where Q is equal to charge, coulombs, C is equal to capacitance, farads, V is equal to voltage, volts. This equation tells us that for a given capacitance, increasing the voltage increases the stored charge. Imagine two water tanks separated by a flexible rubber membrane. When water is pumped into one side, pressure builds up, even though water cannot pass through the membrane. Similarly, in a capacitor, electrons do not cross the dielectric. Instead, energy is stored in the electric field between the plates. This simple idea forms the foundation of capacitor operation. History of the capacitor. To appreciate the capacitor, let's look at its history. The first capacitor was invented in 1745 by Ewald Georg von Kleist. Soon afterward, Peter van Musschenbroek at the University of Leiden independently developed a similar device. This invention became famous as the Leiden jar, the world's first practical capacitor. A Leiden jar consisted of a glass jar, metal foil inside, metal foil outside, a metal rod connected to the inner foil. The glass acted as the dielectric, while the metal foils acted as the capacitor plates. For the first time in history, electricity could be stored and released later. This discovery transformed electrical science and paved the way for modern electronics. Over the next centuries, capacitors evolved from bulky glass jars into compact, highly efficient devices, used in everything from smartphones to spacecraft. Why do we need capacitors? If batteries already store energy, why do we need capacitors? The answer lies in how quickly energy needs to be stored and released. Capacitors can charge and discharge extremely quickly, often in microseconds or milliseconds. Because of this unique property, they perform tasks that batteries cannot. Some of their major roles include energy storage, voltage stabilization, filtering, power factor improvement, motor starting, signal coupling, timing circuits. Capacitor versus battery versus inductor. Many beginners confuse these components. Let's compare them. Battery stores energy chemically, provides electrical energy over a long duration, suitable for continuous power supply, slow to charge compared with capacitors. Capacitor stores energy in an electric field, charges and discharges very quickly, ideal for short bursts of energy and filtering. Inductor stores energy in a magnetic field, opposes changes in current. Widely used in filters, transformers, and power converters. Capacitors are available in different types, and each type is designed for a specific application. Let's briefly understand the most commonly used capacitors. 1. Ceramic capacitor. These are non-polarized, low-cost, and widely used in electronic circuits for decoupling, filtering, and high-frequency applications. 2. Electrolytic capacitor. These are polarized capacitors with high capacitance values. They're mainly used in power supplies, filters, UPS systems, and inverters. 3. Tantalum capacitor. Tantalum capacitors are polarized, compact, and highly reliable. They are commonly used in mobile phones, laptops, and medical devices. 4. Film capacitor. Film capacitors are non-polarized, highly stable, and have low losses. They are ideal for motor run circuits, audio systems, and power electronics. 5. Mica capacitor. Mica capacitors provide excellent stability and accuracy, making them suitable for RF circuits, oscillators, and communication systems. 6. Supercapacitor. Supercapacitors have extremely high capacitance and can charge and discharge very quickly. They are used in electric vehicles, regenerative braking, UPS systems, and energy storage. 7. Variable capacitor. The capacitance of these capacitors can be adjusted manually. They're mainly used in radio and TV tuning circuits. 8. Trimmer capacitor. Trimmer capacitors are small adjustable capacitors used for fine-tuning and calibration in electronic circuits. If you're enjoying this complete capacitor course, don't forget to like the video, subscribe to the channel.